So as already said, my name is Michael Schwarz. Welcome everyone. I'm a faculty at CISPA Helmholtz Center for Information Security, and I'm doing research on CPU security and side channels. There's also my email address. If you have further questions afterwards, maybe just write me an email. As already said before, the chat is also open. So anytime you have a question, you want to know something, I'm too fast, I'm too slow, just write a message in the chat and I should see it immediately. Hopefully it's right in front of me. All right, so what did you sign up for? So what are we going to do in today's tutorial? So you might have seen news messages such as these ones, like we had like headlines out there: Intel Zomyload bug fix to slow data center computers. Zombyload attack lets hackers steal data from Intel chips. Zombyload flaw lets hackers crack almost every Intel chip back to 2011. Why is it being downplayed? Only new CPUs can truly fix Zombyload and Spectre. We have seen that even in TV. That was, for example, CNN talking about Spectre and Meltdown back in 2018. Computer chip flaws impact billions of devices. Or more recently, in 2020, Intel CPUs vulnerable to new LBI attacks. The researchers say Intel processors will need another round of silicon chip redesigns to protect against new attacks. So we've seen the news, and some of us might have read some research papers about that, seen some presentation, but many of these things are more on the theoretic side. So you might know the theoretic side, how that works. But today we're not going to talk a lot about the theoretic side, like how all these things works and why they work. We're more talking about the practical things. So that's why it's called a practical introduction to transient execution attacks. I prepared a bit of code frameworks here that you can download. So the QR code contains simply the URL. You see on the bottom here a link to GitHub, where you can download all the frameworks, including the solutions that we are going to use today. So we will start simply from measuring time, which is already not as simple as it sounds, measuring small timing differences, looking at data accesses, cache hits and misses, building histograms from that, evolving that part into a communication channel that works with the hardware, which is then later on used in a Zombyload attack that we are going to write basically from scratch with all the building blocks that we built before, and then also a Spectre attack. We show that these transient execution attacks are kind of similar to implement. There are not so many differences. And if you have all the basic building blocks that we are going to build today, then this is something that is quite easy if you have one to adapt it to get a different attack here. So I hope that link works. If not, just write in the chat, but I tested that before. So for the things, if you're wondering, can I run that on my CPU? I tested that on Intel CPUs and also on an AMD CPU. So if you have any of that, any recent x86 CPU, then it should work for you, except for Zombyload. Zombyload is a vulnerability only in Intel CPUs, so this will not work. But all the other parts, including the Spectre, works on basically any Intel or AMD CPU. Also for operating systems, I've tested that on Ubuntu, newest Ubuntu. So that works. Anything that can compile C code, has make, should work for you. And I've also tested it on Windows with the WSL 1 and 2. So if you're on Windows and have an Ubuntu there in the WSL, then that also works. So it should work on basically most of the systems out there. So feel free to download the code and try to do the things we're doing live here. I'm going to program live anyway, but it might be a nice thing if you also look at that, maybe have suggestions, maybe you're even faster than I am, and help me out in writing these attacks. All right, so I hope everyone has the link. I can also write it here in the chat again in case you missed it. All right. Then still, we have to start with a bit of theory to know what we are actually going to do. Otherwise, some of this code might not make sense at all. So if you're a software engineer and you're writing code, my code might look a bit weird or even wrong. So we need a bit of theory before that to know what we're actually doing with the code. So first of all, let me start with a definition of what is a side channel. We're going to use side channels for transient execution attacks. Typically, if we talk about a system, then we have some intended communication channels. We want to communicate on our systems. We have APIs, networks, pipes, messages, shared memory, files, and so on. All of these things are intended to communicate. But we might also have some unintended side channels that we did not think of when we implemented our program. And these unintended side channels, they might even leak data that's not intended to leak. And typically, if we talk about side channels, we're talking not about directly leaking data, but we're talking more about metadata. So data that describes the actual data. If you're thinking about a letter that you're sending, then it's not the content of the letter, but the sender and the receiver. That would be the metadata of a letter, for example. And with a side channel attack, we are then trying to infer the secret from this metadata and get the actual data back by only observing the metadata. And this is quite well known if you're talking about hardware side channels, but we're not going to talk about hardware today. We're going to talk about software. And these software-based side channel attacks, they are relatively new. So they were first described in 1996 by Paul Kocher, and we see him again in the end. He's also one of the discoverers of the Spectre attacks. It started with cache attacks, but back then this was mostly theoretic. So it's a great paper, but many things are just theoretic. The real, actual practical attack was then demonstrated in 2005 by Colin Percival. And for all these attacks that we are mounting here that only execute software and infer secret data, we do not have to rely on any bugs. So we assume that all the software that we have and also the hardware for side channels is bug-free. For transient execution attacks, there are meltdown type attacks, we'll come to that. There we are talking about bugs in the hardware, but for all the other attacks, side channel attacks, also with Spectre, we assume that both the software and the hardware is free of bugs, and we only rely on side effects of the software and the hardware of the execution of applications. And we'll see that even if you have these bug-free systems, which is of course not realistic, we still have bugs out there, but even if we have bug-free software, that does not mean that we don't leak any secrets anymore. And side channels, as said, they are relatively new. So if you look at the number of publications here about side channel attacks, so the number of times this keyword of side channels appears in academic publications, we see before like 1996, there's not a lot there, but it increases and it looks a bit exponential, this curve. So side channels, since the discovery, are a thing, and we find more and more side channels and more uses for side channels. So this is also an interesting topic, therefore, because it just gets more relevant in the future. But this about the motivation. What do we need for that? What do we need to mount such a side channel attack purely in software? And one of the most important things is timing. So many software-based attacks rely on timing differences. We're talking about really small timing differences here in the range of nanoseconds. So super small timings. Still, we don't need any sophisticated measurement tools like an oscilloscope or something like that. No, we can purely do that in software. We have software interfaces that allow us to measure timings in the nanosecond range purely in software as an unprivileged application. And with that, we can measure these small timing differences that are either caused by the software or by the hardware. So we can be interested in both. If we talk about some of the timing difference causes, then we see the obvious ones like in software. If we have an application and we typically have some control flow that depends on something. If it depends on secret, then we have different program flows depending on the secret. We might see different instructions depending on a secret. So if you have an if there that goes to different code path for different secrets, like for 0 and 1 bits in a secret value, we see different instructions. We might even see a different number of instructions. So for something, I have to do more calculations than for a different bit, typically a 0 or a 1 bit. So we see differences there. That's quite easy to see. And then we also have timing differences in the hardware. So the runtime of our application that looks like it has no secret dependent things can change on the hardware due to optimizations, invisible optimizations in the hardware. So if we just think about some simple things, if you think about them, makes it quite obvious. If we access data, then it depends where we fetch the data from. Is the data on the hard disk? That's super slow. Is it in main memory? Will be faster. If it's in the cache, a lot faster. If it's a register, super fast. So accessing the same data can have different runtimes depending on where this data is. We also have instructions that have different execution times depending on what they do. For example, if we divide something in hardware using a hardware instruction, the runtime is not constant. It depends on the values that we divide. This is also a small timing difference that we can measure. So let's start again, still at a very theoretical level. Let's start with a simple example about a software side channel, so we can see how that works. And one simple example I really like because it easily fits on slides is a pin comparison. That could be in an ATM, for example. So you have a pin, correct one, and then you have a pin that is compared against a user input something. And if the pin is correct, if both pins are the same, then you get access, for example, to your money. And this can be a super simple, trivial implementation. If you are in your first semester of your studies, if you start programming, then you might write something like this here, this check pin function. It has the correct pin in there, 1, 2, 3, 4. And then a user can input some pin, also a string. And then it goes digit by digit and compares that. And as soon as one digit doesn't match anymore from the user pin and the correct one, then we can already abort, right? Because if one digit is wrong, then the entire pin can't be correct anymore. And that saves time. We don't have to compare everything else if we already know that the pin can't be correct anymore. So then we return the error here. Otherwise, we return the OK and say the pin is correct. Now, this works. This is functionally correct. But now we, as a side channel attacker, could come up with the idea of measuring the execution times for different pins. So we start kind of brute forcing the pins. We start with all zeros and then 1 all zeros, 2 all zeros, 3 all zeros, and so on until we have 9 all zeros. So 10 possibilities. And we just measure the execution time of this pin check function. And then we see we have one outlier. One pin takes longer than all the others. Because if we guess the first digit correct, then the CPU has to do additional work and it has to check the next digit as well. So that takes longer. Otherwise, it can already abort. And from that, we already know something. If we only need 10 tries at maximum to get the first digit. That's the one with the longest execution time. And then we know that, and we can continue like that with the second digit. We know the first one was a 1. So we start 1 all zeros, 1, 1 all zeros, 1, 2 all zeros, and so on. And again, we see one timing will be higher. It takes longer if we guess the next digit correctly again. And in this case, the 1, 2 takes longer. And we simply repeat that for every digit. And we always know when we guessed another digit, that one with the longest execution time is the correct one. Then we guessed correctly. And if you think about that, how long does it take? Yeah, we have 10 measurements per digit. And for a 4-digit bin, with only 40 tries. For each digit, 10 measurements. If we would brute force that, then we need 10,000 tries. So everything from 000 to 9999. It's 10,000. So this simple side channel that only measures the execution time already reduces the number of tries by a factor of 250. So I think that's already a nice example where you can see, okay, with this side channel where we only look at the execution time, we then can infer the actual pin with just a few tries. And the longer the pin gets, yes, the better the factor gets. And for that, we don't need a lot, right? Something I just said earlier, measuring time. That's one of the important things here. So we have to talk about it. How can we actually measure time? Because we'll need that. It's not only for this pin comparison example, it will be for basically all of the side channel attacks. And then for the transient execution attacks we mount, we always need timing, and we need to be able to measure time in the nanosecond range. So one important thing here is that we are not interested about absolute time. So we don't want to know how late it is. We just want to measure differences. We also don't care about the unit of that. We're not physicists, so we don't care if we actually measure in seconds, nanoseconds, picoseconds or something. We just need some time unit. It can be CPU cycles, it can be increments of a variable, something, just something that is monotonically increasing and where we can measure differences. That's everything we need. So that makes it even a bit easier for us as an attacker. How do we do that? If you're talking about x86, fortunately, we have some native instructions for that. On x86, on a bit older systems, we have the RDTSC, and on newer systems, we additionally have the RDTSCP as the read timestamp counter. And that just returns us as the timestamp counter of the current CPU core. What does it mean? That's the number of CPU cycles since the reset, so since we booted the CPU. We're talking about like a 2 GHz CPU, then that means 2 billion increments per second. And we just get the number of increments so far, this timestamp counter. And this is basically the best we can get, because that's how the CPU works. And there are not so many things that are sub-CPU cycling. So when multiple things happen within one cycle. So we get a pretty accurate timestamp here. The unit is cycles, but we don't really care. Which is that we don't care about the unit. And the nice thing as well is, because these are instructions, assembly instructions, they are super low overhead. That's just one instruction that we execute, and it returns the value of this timestamp counter in 2 CPU registers. And then we can simply use it. There is no call to the kernel involved or something like that. So that's extremely low overhead. So that sounds pretty cool. If you have that, you will think like, now it's super easy. We would just use them to measure timing. You can now measure very short timings. For a 1 GHz CPU, one cycle is like 1 nanosecond. So that's perfect for what we want. But does it actually work like that? Can we readily use that? And the thing is, if you try to use it like that, like the naive way of using that, we use the RDTSC, then we execute something, we use the RDTSC again, and then we calculate the difference. Do we really get the runtime of the function with that? And it turns out it's a bit more difficult in reality. So in theory, yes, we would get the runtime of the function. But in practice, that's not really the case, because our modern CPUs have out of order execution. We'll also talk a bit about that later on when we're talking about the transient execution attacks. But for now, like, CPUs can reorder instructions, so they don't have to execute them in the same order that we define them in our application. And that means if we write that code, there are different possibilities of what can actually go on. So the CPU might consider like, okay, I have some other instructions here. I move them before the second RDSC call. So we not only measure the runtime of the function, but also something unrelated with that. Or the CPU might decide, okay, let's move the function out of the RDSC because there's no dependency. I can reorder that and instead move something else between the two RDSC calls. Then we measure something completely unrelated that has nothing to do with the function we want to measure. Or the CPU decides like, oh, I can do this, the two RDSCs right now. So executes the first, the second, and then starts executing the function. And then we basically measure nothing. There's nothing in between. So that will be pretty constant difference that we get here, except for the interrupts that occur between the two RDSCs. But we already see we can't really rely on that if we just have RDSC function, RDSC, to actually measure what we want. But we still need that. So luckily, there's also a solution for that. The RDSCP, that is on more recent CPUs already in there, is pseudo-serializing. So that already prevents some of the reordering of the CPU, because also Intel saw like, okay, it makes not a lot of sense if you have that function to measure accurate timings and then it gets moved around everywhere. So there's this pseudo-serializing RDSCP that can't be moved arbitrarily anymore. There are also serializing instructions. For example, if we don't have them, maybe some older CPUs, then we can also add some serializing instructions ourselves, like a CPU ID instruction that also ensures that the CPU does not reorder our things. CPU ID, however, is a bit a high overhead function. So that has like 100 to 300 cycles, depends on the system. So we don't really want to add that. It adds a lot of overhead. So we can also go for some lightweight serialization like fences. An end fence also ensures that things can't be arbitrarily reordered by the CPU. And this is a lot of things to consider. And there's actually a white paper from Intel that just talks about measuring execution times. This multi-page white paper that explains exactly these things, what can be reordered, what do you have to do to serialize that, where do you have to add the fences, which fences do you have to add to get the perfect measurements there, then how to get rid of the overhead of the fences again. So this is actually a really complicated topic, although it's just measuring time. So there's a question in the chat, doesn't the volatile keyword help against out of order execution in C? The volatile keyword is something that is only related to the compiler. So if that can only give hints to the compiler and tell the compiler that there might be different code locations that the compiler can't see where this variable is changed. So you destroy some of the optimizations because the compiler has to assume someone can change that in parallel. At CPU level, you don't see that keyword anymore. So at the CPU level, this keyword doesn't exist anymore. And we're already down, we are compiled, we are at the instruction level, and the CPU has no idea about the language that we wrote that in, compiler hints. It doesn't even have an idea about different applications. That's just a stream of instructions then for the CPU that the CPU can reorder as the CPU sees fit, what best utilizes the CPU, the execution units. Okay, but it's a good question, of course, and something that gets easily confused. Yes, so of course we don't want to read this entire white paper now. That's why we are here in this tutorial. And that's why one of the variants that's kind of lightweight and that turned out to work quite well is simply adding M fences before and after the measurement. That might be too much overhead, but at least it works reliably on basically all the systems. So we have then an M fence, an REDSC, an M fence, then our function we want to measure, another M fence, REDSC, M fence. And that prevents the CPU from reordering most of the things here at least everything that is typically relevant. So we see just measuring time is already quite tricky, but we can solve that. And this is like the practical way to actually measure time that we will also use today. So now that we have this primitive for measuring time, we want to, of course, measure something, right? So we want to see, does it work? Can we really see small time differences? So let's look at something that we can measure with that, where we can actually write that in code and see how it works. And one of the things that is easy to measure and that works everywhere and that we need a lot is measuring data access timings. Something I've already hinted in the beginning, where I said, like, it depends where the data has to be fetched from, the timing, the access time is different. And if you looked at like a super high level detail of how a CPU core works, then we have an execution engine, a front end, and a memory subsystem. And execution engine executes our instructions, and some of them need access to the memory, like instructions that load or store. So the execution engine is connected to the memory system, and depending on what it wants to do, load or store, there's also a buffer in between, a load buffer or a store buffer. They're then connected to the L1 data cache. It's also connected to the data TLB. We don't care about that. And then the L1 data cache is connected to the L2 data cache, or in most cases, a shared cache. So it contains not only data, but also instructions. It's like a combined cache. And they are connected using another buffer. So they're not directly connected, but all the communication goes through the line fill buffer, the LFB here. And then we also have the connection from the level 2 cache to the level 3 cache. And then the level 3 cache is connected to the DRAM, so it's access to the DRAM. So this is our entire memory hierarchy here that we can see. We can already think like, okay, depending on where the data is stored, it takes a while for the data to travel back to the execution engine. For example, if you have a load. And this is really something that has measurable timing differences. So the cache is, of course, fast, memory slow. Then if we go out of the memory, then it becomes extremely slow. So loading from disk then typically also goes through the operating system. That will be extremely slow. And if it's not even on disk, but it's somewhere on the network, then it's very, very slow. But we don't even care about these cases anymore. We're only caring about cache and memory for our side channel attacks in most cases. And if we look at the numbers, like how long does it really take, then we can look at the numbers that, for example, Intel provides for some recent CPUs. If you have data stored in a register, then that's super fast to access between 0 and 1 CPU cycle. Depends on what exactly we want to do with the data. If we just move it from register to register, that's typically for free. But other operations might take 1 cycle. If it's in the first level, the L1 cache, then that takes 4 cycles. That's still quite fast. Next level, as we've seen, it has to go for the line fill buffer. Then we are in the L2 cache. Then we are around 12 cycles here. That may be plus minus 2, depending on the CPU. If we then have to go to the last level cache that's also shared across all the cores, then we are in the range of 26 to 31 cycles, depending on where exactly it's stored in the last level cache. And if you then have to go to the main memory, that is really super slow for the CPU. Then we are talking about 120 cycles plus. So that can be 2, 3, 4, 5, 6, 700 cycles, depending on your CPU speed and your memory speed. So we see these are huge differences. And we already know with RETSC, we measure in cycles. So we could even distinguish like register L1 because we get single cycle differences out of that. That's already interesting. And that is something that we want to do. Not register and L1, but cache and not cache. So if you look at a typical cache, a CPU cache, then we first need to talk a bit about the high-level functions. So when is something even in the cache? When is it not in the cache? And for that, I have a very simple application. Let's call it application. That just does a printf, so it prints the value of a variable. And the first time we execute that, we need to get the variable I, the value of that. And we haven't used it before. There's nothing before in this application. So it's not in the cache. The cache only stores copies of recently used things. It's not there. And it has to be requested from the main memory. And then the main memory has the value, responds with the value, and the cache transparently stores a copy of that value in the cache. So the next time we have that printf in the next line of our code, we again need the value of the variable I, but this time the cache already tells us like, yes, I have that. Here you go. I have a fresh copy of that. And we don't have to go to the main memory, do the entire request response cycle again. So we see in the second case, we don't need to do that. And that obviously makes it a lot faster. So the second case is fast. The first case where we have to go where the cache tells us, no, I don't have that, and request it from the main memory. And the main memory responds, we've seen latency of the main memory of more than 120 cycles. This is slow and that takes longer. Something that we can measure. So we see here that the cache already works transparently. So everything we access automatically lands in the cache. There's some exceptions to that. Pages can be marked as uncacheable, for example, but generally everything that we access, doesn't matter if we read or write, if it's data or code, gets a copy in the cache. And this is also what we have to rely on. So the CPU actually does that. There's not really an instruction to force something into the cache. You can only tell the CPU like, please put that in the cache, that's important, but nothing to force it into the cache. Because if we access something, it gets into the cache anyway. But in contrast, we have something to remove data from the cache. Because if you think about that, everything we access gets into the cache. It has to be removed. Yes, this is done automatically again by the CPU. So if there's no free space in the cache, then something has to be evicted, written back to a different cache level or the main memory to make space for new data. But we can also do that manually and flush specific data from the entire cache hierarchy. On x86, this is an unprivileged instruction, the CL flush, the cache line flush. And this instruction just gets an address, virtual address, and it removes from all the cache levels, L1, L2, last level cache, the data from the caches, but ensures that everything, that we don't lose data, that everything is first written back to memory if the contents differ. So if we have writes to the cache, for example, it also ensures that the writes are then populated back to the main memory. So we don't lose any data. That would be really bad. And then it's gone from all the cache levels. And the next time we access that data, it has to be fetched from the main memory again. And if you access that, it's again populated to the caches. Next time will be cached again if we don't remove it again with the flush, the CL flush instruction. The CL flush instruction is also quite easy to use. As I said before, it's just this one instruction that we can use in assembly. So if you're writing C code, there's no C equivalent for that. Depending on the compiler, there might be an intrinsic, but we can simply use inline assembly here, CL flush, and then the address we want to flush, and then it's removed from the entire cache hierarchy. So now we have the two parts that are interesting for our measurements. We know how to get data into the cache, simply accessing it, and we know how to get data out of the cache again by using the CL flush. And now we can use that knowledge to measure something. How long it takes to access data in the cache and how long it takes to access data that is in the main memory and not in the cache. And for that, we look at the two cases and build measurement code for both cases. So the first case, we want to know how long does it take on our system to access data that is in the cache. We simply build a loop where we get a timestamp. We have RETSC for that. Then we access the variable, you read from it. We know the first time it will be put into the cache, then it stays in the cache if we access it all the time. And we get a timestamp again. And then we look at the difference of the two timestamps. That's how long it took to access the data, and build a histogram with the difference. So look how long it takes, and then we look at a nice distribution. And the second case, we want to measure how long it takes if data is not in the cache. Very similar, but of course we have to get it out of the cache before. So we first flush the variable from the cache, then it's not there anymore. Get a timestamp using RETSC, access the data. We know it's not in the cache, we just flushed this before. Get a timestamp again, and again update a histogram with the time difference here. And if we plot that, we get something that looks like that. So all the cache hits are here around 60 cycles. Why is it that much longer than the numbers I said before? That's because we added all these M fences that have quite some overhead, but it's fine. It just shifts everything. Doesn't matter for us. So we see the cache hits here, and we see all the cache misses where we have to go to main memory. Somewhere here, far on the right, is more than like 320 cycles. So there's a huge gap in between. And if we just look at the timing of the access time, we can already infer whether the data comes from the main memory or from a cache. Now I explained that to you, and you said like, yeah, nice in theory, but probably that doesn't work. So let's start with the first coding example here. So let me switch to my code view. All right, so I hope you can read it. Here's a question. So would it be correct to say that the variance in the histogram, particularly for cache hits, comes from fences? So the variance, so we see the shift because we have seen cached access, for example, if it's in the L1, it's like 4 cycles, L2, 12 cycles, L3, 20, 30 cycles, and we see here around 60 cycles. And this is not the variance, it's just the shift because we have the RETSC, then we add an M fence here and an M fence after that. And maybe we do this access in a function call, depending on what the compiler does. So we measure additional constant things with that. An M fence takes around 20 to 30 cycles. So that sums up. We measured 2 M fences with the RETSC. So we get a plus of like 60 cycles. The variance, switch back here. We also see a slight variance here, like it's not always exactly the same time. This is typically not from the fences, but we have interrupts. So these are typically moving everything to the outside, so we don't see them here, but on the far right, you'll also see some timings if you had interrupts in between. But other than that, reading the RETSC, it depends a bit on the CPU you are on, how often this is actually updated. So it increments with every CPU cycle, but not all CPUs expose exactly this update every cycle. So for example, on older Intel CPUs, you only get, if you read RETSC all the time, you don't get every value, but only in steps of 2, 3, or 8, for example. So this is also why we see the variances here. If you're on an AMD CPU, there's new CPUs even worse. So you have updates every 30 to 40 cycles only. So you have for the start and the end variances, and that adds up to this Gaussian curve that we see here. Does that answer the question? Okay, perfect. All right, so we now want to actually do that. And this is if you've downloaded or opened the code. This is like the first example that we can do here, measuring access times and building this histogram that we have seen on the slides, showing that it actually works. And I've already provided a skeleton so that we don't have to write that much code. And it's basically, we want to have one function that measures how long it takes to access memory. So we want to have exactly what we had on the slides. We get timestamp counter for the start. Then we access an address. We get the timestamp counter at the end. And then we return the difference. So, and you already see I'm using some weird functions here, RDTC, maccess. We see that here it's the header that's also provided here, the cache utils, and that already had the things that we've seen on the slides wrapped into C functions so that we can use these assembly instructions directly in C. You see we have the RDTC here that uses the mfence, RDTC mfence, and returns the timestamp counter. We have this flush here that flushes something from the cache, and we have an maccess that just loads data. You could, of course, also do something like simply dereference the data, but that might get optimized away by the compiler. Someone already suggested we could make it volatile here. I usually don't trust the compiler too much for these things because, as we see here, the code doesn't make a lot of sense, and the compiler might say like, okay, you dereference that, but you never use the value, so why should I keep that? But if you write it in inline assembly, then the compiler can't optimize it away. That's the only reason we have that here in inline assembly, but that does nothing more than taking a value from the memory, storing it into a register. So simple load. So we have a function that now measures the access time to a variable. Now we want to measure the cache hits. As we have seen the first case on the slide, we build a loop for that. So size here. So we iterate the number of measurements, and in every measurement, we just want to measure cache hits. So we call this function measure access time for our address. And if you just access that all the time, first time it will be copied into the cache, and then it stays in the cache, and we always measure how long it takes to get it from the cache. What do we do with this hits then? We have to store that in a histogram. So if hit is smaller than the histogram entries to avoid buffer overflows, then we update the histogram at hit and add 1 to this case. Then we have the same thing for the misses. So we can start by copying that here. Call it miss, but now we want to measure misses. So we also have to ensure that we don't have it in a cache anymore. And conveniently, we already have that flush function here. And we can simply call that flush function on the address. Then it's not in the cache anymore. And then we measure the access time to it. Again, update the histogram with the time it takes for this now cache miss. And that's it. If you look at the remaining code, that's just code around that. So it opens a log file to store all the measurements there. And the time, the hit and the misses. It allocates the data that we want to access, where we want to measure the data. Then it calls the measure hits and measure misses function. So we have the two distributions there, the two histograms. And then we go through the histograms, scale them. So we combine the entries a bit to not have too many entries printed out on the console, and store the entries in the file so that we can now later on plot it nicely using Python, and also directly print it on the terminal. And that's basically it. So it's not a lot of code. And if everything works now, it should kind of look like what we had in the slides. What about switching off compiler optimizations? Yes, compiler optimizations are a super interesting topic in this area. That is why many people decide to write all the critical parts completely in assembly. I don't like to do that because it just takes a lot more time. And if you know what the compiler does, you don't have to do that. So if you switch off optimizations completely, you don't have the problem that the compiler removes stuff, but you have a different problem. The code is really inefficient because without optimization, GCC and also Clang do weird stuff. Like if you have a register to register copy, they typically go over the stack. So they copy it to the stack and then load it from the stack again to the different register. And this is okay for many things, but for many other cases, it's not okay. So if you're talking about transient execution attacks, then we have a really, really tight window where we have to do all the things, leak the data. And if you have additional memory loads and stores, then that doesn't work anymore. So critical parts have to be written in assembly. For the others, to ensure that we don't have other effects in there, we typically use some optimizations. So a good optimization parameter is optimized for size. That gets rid of the additional instructions, but it doesn't remove too many things in there. So that turned out to be a quite good trade-off with OS. I call it optimized for side channels. The S is for side channels then, and that works quite well. But if you're going up to 03, then the compiler starts doing weird things, reordering, removing stuff that again destroys your attack. If you go down to 00, you get additional effects in there that might be not good in some cases. In others, we don't care, but in some cases, it breaks the attack. Okay, let's build that and see if it runs. Okay, we get an output. Let's see, on the left side, we have hits. On the right, we have misses. The leftmost column is the time, the X is time. And we already see a group here. You can nicely see that, like many access times for a cache miss are around 310, 325 cycles. That's plausible. And if we scroll up, yes, for the cache hits, we are here around 400, 500 are the number of events we have here at 100 to 115 cycles for the cache hits. And before that, nothing. So this on the terminal is not as nice, but we can also plot that. It's also a plot script with that, yes. And then we get something that is very similar to what we had in the slides, where we have the cache hits on the left side, a large gap in between, and then the cache misses on the right side. So we see we can actually measure that. And the code for that was not too difficult. Then we can also calculate like threshold. We can say, okay, if the timing is below something like 200, then we are sure if we see that, then it's a cache hit, because we don't see any misses below 200 cycles on this system. That, of course, varies depending on the system. There's another question. I'm probably not the only one observing this. The histogram on my machine is missing a clear peak for the cache misses. I guess this is due to the noise of Zoom, etc., as it works on a more noise-free machine. Probably yes. So if you're running on Zoom or listening to music in the background, streaming a video, things like that, you get a lot more noise, and that also evicts parts from the caches. Your scheduling is not perfect anymore, so you might be interrupted many times. Then the histogram looks a bit worse. So here I'm the demos here, the remote programming is on a remote machine here, not the one where Zoom runs, to make everything a bit more stable. So here it looks much nicer, but it can be that on your system you get a bit more noise and maybe even overlapping histograms depending on your CPU model, your memory speed, and so on. But generally, you should get something that looks similar to this histogram. So if you just want to look at the result, don't want to code that, the solution is also included. You can also run that by make solve that compiles the solution, and running that should give exactly the same result here. Yes. So we've seen just a bit of code, some assembly instruction wrapped into C functions, and then just a few lines of C, and we can already see the differences between cache hits and misses. So you might say, okay, that's nice, but can I do something with that? So what am I going to do with that knowledge that I can distinguish a cache hit from a cache miss? This is one really, really important building block for then the transient execution attacks, but also for something before that. We're building the next building blocks for our attacks. And this building block is called Flush and Reload. And it again exploits the cache. So if we have two applications, an attacker, a victim, and we have some shared memory between the attacker and the victim. And that can be something like a shared library, like the libc on the Unix systems, that's basically in every application. Then they share that memory. And if it's cached for one application, it's also cached for the other application. So it's how caches are designed for shared memory. It's cached for all the applications that share the memory. And now as an attacker, I can simply flush the shared memory. I have access to that. It's also mapped in my address space. And that's not in the cache anymore. We already know that. Now, if the victim is scheduled and the victim accesses the shared memory, then we also already know that the CPU puts copy of the data into the cache. So it's cached again. And if I'm now, it's my turn as an attacker, I can simply access the shared memory and measure the access time to the shared memory. And then I get two cases. Either it's a fast access time, then it's a cache hit. It's already in the cache. And we know we removed it from the cache. We didn't add it back to the cache. We know that the victim must have accessed this data and it's in the cache. And we know that the victim used it. If it's not in the cache, then we have a cache miss. We see that in a longer timing, and we know that the victim has not accessed that data. So this is this primitive of flush and reload, and we've already seen the basics of that in this first coding session here. And flush and reload is a really nice side channel. So it gives you this information whether some data was accessed or not accessed by someone else. And this is extremely accurate because we do that on a cache line granularity. So we can monitor 64 bytes of data if they've been accessed or not. It's super fast. Getting time is fast. Flushing is quite fast. So one cycle of observation is around 300 cycles. We typically don't get false positives because data just does not appear on its own in the cache if no one accesses that, except for prefetching. But typically, we don't have false positives. But it also has a disadvantage. It requires shared memory. So we can only attack an application with which we share memory. So for an attack, it might be a bit of a limitation, but we can do something else with flush and reload where we don't care about that limitation. And that's a covert channel. And that's a simple, really simple form of an attack. What is it? A covert channel allows two processes to communicate with each other, although they are not allowed to communicate. So there is no intended communication channel. There's no way, for example, because they are not allowed to do so, there are some policies, or there simply is no interface or a firewall blocking that, something like that. So we don't have a communication channel and we still want to communicate. And if they're running on the same machine, then they share the cache and we can use the cache as a communication channel with our flush and reload. So in our case, both the sender and the receiver are controlled by us, so we can do whatever we want. And we will use that to communicate using flush and reload. So we have the cache, we have the sender, we have the receiver. And then we simply use different pages for every letter we want to send. So if we want to send, we're talking about byte-wise communication here. So we have like 256 different pages. And depending on what byte we want to send, we access one of the pages. If we do that, then this page is, or it's part of the page, the first cache line there, is cached in the cache, the others are not. And then the receiver can measure that again. So the receiver starts. Thanks for attending. The video, I think, will also be available afterwards. So if you're still interested, feel free to look at the recording afterwards. So the receiver starts and flushes all the cache lines of all the pages. Then nothing is in the cache. And now if the sender wants to send, for example, a G, then it accesses this page, so page number hex 47, and the cache line of this page will be in the cache. Then the receiver goes through all the pages and measures the access time for all the pages. And for this one page that was cached by the sender, it will be faster. Of course, it's a cache hit there. You will only have that for one of the pages, and then the receiver knows, okay, this cache hit was on page number hex 47, so this must be a G that the sender sent. And then the receiver flushes again all the cache lines, and the sender can send the next byte, and so on. So with that, we can use the cache access times and the cache misses, the memory access times, to encode data and transmit data from one application to different one. And we want to do that now, because that will also be an important building block that builds upon the first one, and that we will need for our transient execution attacks then. So we have a sender and a receiver. So let's start with the sender. We again have some helping functions here, the same as before. So we have the RETSC, we have the flush, we have the access. Then I already implemented the flush and reload, but you could have also done that. That's exactly what we've seen before. So we measure the access time and then flush afterwards. Also do it the other way around, doesn't matter. And then we have a reload only function that measures just a cache hit. Because with that, basically already implemented for you the exercise 1 here in this calibrate flush and reload that measures cache hits and cache misses and then gets the threshold for you. So we don't have to do that all the time. That's now implemented already in the cache utils here. For the sender, we have some input thread running that gets keyboard input from us. Then we have a shared memory channel, a file called transfer that we map into the application. And then we just want to access, as we've seen in the slides, exactly the page that corresponds to the character we entered. So we have something like an access. Channel is our shared memory. And we want to exit that at, so how's my character called? ToSend. ToSend contains my current character that I entered on the keyboard. And I multiply that with 4096 page size. So for character 0, I access the first page of the channel, for character 1, the second page, and so on. So this is our simple sender here. Just access a memory page depending on the input. But then we, of course, also need a receiver. And in the receiver, basically have the same setup. We calibrate this threshold so that we know which timing corresponds to cache hits and misses. We again have the shared memory here. And then we all the time do this flush and reload attack, as we have seen, on all the pages. Where you can access the video of this tutorial later, I honestly don't know, but I guess that will be announced somewhere on the web page. But I don't know. You have to ask the organizers of ESORICS for that. So what you have to do here is we go through all the characters. You might see these weird calculations. That's just a part for A and D to confuse the prefetcher. But we go through all the pages and check if the first part of the page is cached. How do we do that? We do this flush and reload on the shared memory for character times page size for every page. And we check if this timing is below, calibrate that, cache miss. If this timing is lower than a cache miss, then we know it's a cache hit. And what we can then do is we check that this character is not the same as the last character to not spam our output. Then we print the character. Flush that here as well. So it's displayed immediately and set last character to character. All right, that should hopefully work. Let's see, simple flush and reload, the same thing as we did on the slide. Does it compile? Yes, it compiles. So now I need the two applications. Start here, channel encoding, start the sender here, character to send, E. No, let's write ESORICS. And here, to make it a bit more stable, that often helps is to pin an application to a core to prevent the scheduling. Then we have here the receiver. It already sees an E. That is good. Now enter the next character. S. Works. SOR. Nice. And we see our sender just accesses a page depending on the character we input, and the receiver checks which page is in the cache, and from that infers the character that we entered here. Now should we write something? 2021 works. Nice. All right. So we already implemented a communication channel just via the cache. Again, wasn't that difficult. So we already knew the basics, measuring access times from the previous one. And now we just combined all and calibrated it automatically, not looked at the histogram, did that automatically. We can also see that here, the threshold it calculated was 159. So if it's below that, it's a cache hit. All right. So now we have great primitives. And we can covertly communicate, but still we don't really leak any data. We want the precious data here, not only metadata. So with flush and reload, we can see if a different application accesses some memory or not, but we don't see actual values. And this is what we want to do now. So in this part here, we want to go from metadata to actual data to these transient execution attacks. And for that, we are back at out of order execution. So it's out of order execution that already annoyed us with the measurements, the timing measurements. But now we're going to exploit it. So if we, again, a simple example, look at that code, then now we are talking about compiler out of order, something that we can prevent with volatile. If we look at that code, we are calculating the diagonal and the area of a rectangle. And if we look at that code, then we see some of the parts have dependencies and some have no dependencies. So we can calculate the diagonal and the area independently because they have no dependencies, but the printf has to wait for the diagonal and the area to actually output that. So there or these things that we can see on the source level. On the hardware level, the CPU does that. So if you look at the, this is like a simplified overview picture of a modern CPU with the front-end execution engine memory subsystem, and the CPU fetches and decodes the instructions in the front end. So everything we have in our code, instruction by instruction. And then it moves it to the back end. And then we don't have our order anymore. When moving from simple examples to questionnaire to leaking secrets from an actual application, for example, crypto libraries, are there any additional things we need to worry about? For example, how to minimize noise in the measurements? Yes. So if you attack huge applications, then noise is always a problem. So it depends on your attacker model, what you can do. So are you a privileged or an unprivileged attacker? Typically, you're an unprivileged attacker, just executing code. There you can't do a lot about the noise. What you have to do then is basically repeat the measurements as often as possible, because noise is kind of random or pseudo-random. And the signal that you have is always the same. So if you do a lot of measurements and average, the noise averages out because it's statistically independent from the signal, and you just need to do more traces of the same thing. So this is typically the thing. If you're an unprivileged attacker, you collect many traces, average them, and the independent noise, you lose that, and you're left with the signal. In case you are a privileged attacker, and that means, for example, if you're attacking a trusted execution environment, or if you're running inside a virtual machine and can have root access there, then things are different. Then you can do more things to avoid noise, because then you're basically the operating system can ensure that the scheduling doesn't interfere with your attack. You can pin applications yourself and other applications to core, ensure good co-location, shut down all the other applications that you don't need. And this makes it a lot easier to get noise-free measurements. But still, also in normal attacks, it's not a lot more complicated than the simple examples that we have. You just run them many times and average them. And then you still get the signal out of that. The more complicated thing often is to know what part can we attack, and does it provide enough leakage that is worth attacking. But for we'll also see that here then for Zomyload, for example, we don't really have to deal with a lot of noise there. So back to out of order, we have these instructions in the front end dispatched to the back end, and then the back end doesn't really care about the order of the instruction anymore. It just schedules that on the individual execution units that we have in the CPU, with multiple execution units, for example, for arithmetic instructions. So many of them, if you don't have dependencies, can be executed in parallel. So all these instructions are executed out of order as long as their dependencies are fulfilled. Otherwise, they have to wait for the dependencies to be ready. But that also means if you're executing them in any order, that some instructions are already executed before others have been executed, and there might be some in between that haven't executed yet. So that would be extremely confusing as a programmer and for debugging and things like that. So if we are done in the back end, the CPU still retires them in order. So for us, it again looks like as if they were executed in order, because only the instructions can only retire, so can be visible if all instructions before that have been retired as well. And then it appears to us again as if everything is executed in order, and that is what we architecturally see. Now we have one problem, and these are exceptions. So if we execute out of order, and at some point we have an exception, then we can't really stop there, because it doesn't, for us, it should look like as a programmer that this wasn't executed yet. And if something throws an exception that is not even visible yet, that would be confusing and also broken. So we can't, in the out of order exception, really handle exceptions. We just mark something at we throw an exception, and we check that when we try to make it visible. But it also means that we can have exceptions out of order that are not immediately stopping the execution. And then the CPU simply flushes everything it did after that and recovers the state, and everything looks fine from an application perspective. So this is an interesting behavior that we are going to exploit for attacks. Because we know that instructions after an exception cannot be retired because the exception stops the execution. So we also can't see the result, obviously. That's a good thing. That is necessary to make it architecturally, functionally correct. But they have been executed, and that also means that they used resources like the cache. So what happens exactly when something like this happens? We have some instructions that executed after an exception, and for example, that loaded some data. And we know if we load data, it will be in the cache afterwards. Do we have these side effects? And if so, can we observe them? And we already know we have these primitives with flush and reload now that we can see if memory was accessed. So let's start with a simple toy example to see if this is even a possibility. So we write 2 lines of C code. The first one, now we finally have the volatile keyword here. We access a null pointer. Could also be maccess null here. And the null pointer on modern operating system is invalid. So this raises an exception, a segmentation fault, and the application has to stop here. And in the next line, we access an array at page 84. So something we did in the Covert channel before as well to transmit data. And now we can look, can the receiver see that? Can the receiver see that we accessed page 84? Although the sender crashed before, it never really accessed it. So we look at this flush and reload over all these pages and we see, yes, the receiver actually sees that this one is cached. So this unreachable code line was really executed and left traces in the cache. And afterwards, the exception was thrown, our sender crashed. So we see that the out of order instructions really leave traces in a microarchitecture, for example, in the cache. And we call such instructions transient instructions. So instructions that were never made architectural, but still left some traces because they have been executed in the out of order execution or in speculative execution, as we will see with Spectre. So you can also try that in the example, try to crash it before, and you will still have this cache hit in the receiver. So can we do something with that knowledge? So we have these transient instructions all the time because we always have out of order execution. And we've seen if we do a crash, then we also get this out of order execution and do something, but our application crashes. And yeah, then it's kind of boring working with that. If after every memory access, we have to restart our application. We could, of course, do that, but we could also try to prevent a crash. So because we will need that then for a Zomyload attack, we want to access data where the application typically crashes because there's an exception, but we don't want to restart the application all the time. So can we prevent that? And the answer is yes, we can do that. Actually, there are multiple ways of doing that. So we can handle the fault. That's something we'll look at right now because that works basically on all systems. We can also suppress the fault. There are hardware extensions like Intel TSX that if you wrap your exception with Intel TSX, then this fault never occurs. It's just notified that there should have been a fault, but that requires this hardware extension Intel TSX. And we can also do fault prevention. So we can ensure that this exception is never made architectural if it stays in the transient execution, for example, using branch mispredictions, then we also don't crash. But we are now focusing on fault handling because that's something that is easy, reliable, and works in all the systems. Given the time series graph in slide 30, you just show, would you explain the spikes and outliers, what they mean? You mean this one probably, because 30 was, yeah, 39. Yes. So the large spike here is the cache hit. The others are the cache misses, and there we see some of the measurement noise. So as said before, RDSC, depending on the system, doesn't update with every cycle. So you always get plus minus up to on Intel up to like plus minus 8 cycles. So your start time is plus minus 8, your end time is plus minus 8. If you subtract that, you also get a Gaussian distribution that varies a bit. What you have as well on your system is that your CPU frequency is not fixed if you don't fix it. So that also goes somewhere between 800 megahertz and your turbo boost, which might be 5 gigahertz, depending on your system. So the CPU frequency changes. So all these things have small effects on the access time. And this is why this is not a straight line, but why we have small differences there. But still, we see a huge difference between everything that is on the top, a miss, and everything that is below, a cache hit. What does it mean, cache hit, from point of view of the attacker? So if we go a slide back, this is what we executed. So we accessed this array at only one page, at page 84, the same that we did before with the sender and the receiver. When we send a letter, that might be ST, something like that. Then we also access like array page 84, and this is then in the cache. And we are still here, all this attacker controlled. We don't have a real attack yet. We're just building our building blocks. We just see, okay, even if we crashed and this code line was never accessed, this code line was executed transiently and led to the data caching of that array. So that was just a demonstration that even if you don't architecturally see that a line of code is executed, it is executed out of order and the effects still remain. Yes, so in our case, we are still, everything is attacker controlled. They communicate. They have this array which is shared memory, and they can both access that and see the same pages. So we are not exploiting anything right here. We're just looking at things and see how we can then exploit, because we are still missing this one primitive here where we say, okay, we want to have something that crashes, but we don't want to actually crash the application, but continue. So we need to handle that fault, because right now, when we execute that code, our sender here simply crashes because the null pointer exists. So going to the code here. Signals. We want to ensure that we, even if we access something that we are not supposed to access, like a null pointer, that we can still continue in our application, continue executing and not being terminated by the operating system. So we can do that using signal handlers on Linux here. On Windows, we can do something like structured exception handling. It's similar, so we can do this, do similar things here. So what we have here is a skeleton, is an application that has a function can access, and can access should return if we can access an address or not, if it's an invalid address like a null pointer. And right now we try like can access main, so we try to access our code, that should work. Accessing null, dereference that here should crash, of course. Accessing a kernel address should also crash. So if we compile that without doing anything and running it, then yes, we can see accessible main, can access the main function, we can dereference that, load from there. But if you try that from a null pointer, it doesn't work anymore and we are faulty. But we don't want to fault, we want to continue because we want to experiment with that. So what we have to do is to implement a signal handler. So what we do is we have to set up a signal handler telling the operating system when there is an exception, like a segmentation fault, we want to handle that ourselves. We don't want to get killed. So we tell the operating system, if there is a segmentation fault, then don't kill us, but jump into the Segfault Handler function. All right, in the Segfault Handler function, we want to ensure that we can get more segfaults, not just one. So we also unblock the signal again, unblock signal, seg_v. But that still we have to do something, right? We have to handle that access because otherwise we retry and retry again and it will always fault. So we need to do something. We need to restore the program state. So we want to kind of save the program state before we do the access, then try the access, we are faulting, and then we want to restore our state and skip that instruction. And for that, conveniently, there are C functions with set jump and long jump that can basically do this, like save parts of the application state and then restore that. So we can write something like set jump, so that saves our application state here. And then we access what we want to access. And if it worked, we return 1. If it faults, if this access faults, then we jump into the Segfault Handler, say, it's fine. We want to have that exception here. And basically, we want to restore the state. So we do a long jump here. This long jump goes back to the set jump, but now with a different return value. Then we go here with the kind of old state and skip that if, and we land after the if, and here we return a 0, saying, okay, we had to skip that part in there, it didn't work, we crashed, so this address is not accessible. So that's a bit of a weird construct here, but it turns out that works quite well. And if we now run that, it doesn't crash anymore. We see we can access main, returns 1. So we could access that and return afterwards for the other two addresses, null and the kernel address. We crashed, went into the Segfault Handler. The Segfault Handler just jumped back after the access, and then we returned with the 0 code. And see, it is not accessible. So now we also have a primitive to access data we are not supposed to access, triggering normal segmentation faults, and still continue with our application. And this is also a really nice primitive that we are going to use for our attacks. So yes, we have, because now we have everything that we need to build our first transient execution attack, a microarchitectural data sampling attack. So what is this MDS, microarchitectural data sampling attack? What does Intel write about that? Here say fill buffers may retain stale data from prior memory requests until a new memory request overwrites the fill buffer. Under certain conditions, the fill buffer may speculatively forward data, including stale data, to a load operation that will cause a fault assist. Interesting. So we will get stale data under certain conditions from the fill buffer. If we remember from the memory hierarchy, that is the part between the level 1 and level 2 cache. Under certain conditions, we still have to figure out if there was a fault. We know faults now, we can handle faults. So we just need the certain conditions. And then we get speculatively forwarded data. So in the transient domain, we also know if you're in the transient domain, we can still encode data in the cache and then restore it afterwards. So what we are going to build now is the ZombieLoad attack that does exactly that, what Intel described in this deep dive afterwards. So how does it look like? We are starting with a simple memory page. We're interested in one cache line there. And we have an address, a virtual address to this page. And accessing that page must fault. Okay, so it must throw a segmentation fault, for example. And this is basically what Meltdown does. And this is what we kind of already have with the last example, where we try to access a kernel address. A kernel address is an address that maps to a page that belongs to the kernel. So we get a segmentation fault because we don't have the privileges to access that. And this is basically this setup, and this is exactly what Meltdown does. We access a kernel address, get an exception, but before everything goes to hell, we handle that exception, encode the leaked value into the cache, and recover it from there. But we're not interested in Meltdown now. We're talking about Zomyload. So we have one page and a faulting load to that page. So it must be, for example, a kernel page. And then for Zomyload, we have a different address, different virtual address mapping to the same physical page, and now one that we can also access that does not fault. Now we have this certain condition, and this is basically flushing the cache line on this page while we access it using the different address that faults. So weird combination that should never happen in a normal application, but something we can easily build. If we have that scenario, then we flush one cache line, at the same time access that. So we load it into the cache, remove it from the cache, already complicated, and then there's an additional fault for loading that. So complex condition, and then bad things happen. And what bad things are is that we get old value that is stored in the fill buffer, and we can transiently use that. So we form this faulting access where we load from this address that faults, we get a value. And we are dying here. We handle the fault then, of course, but the CPU architecturally does not execute any further, but out of order it executes further, and we can use that value that we received from the faulting memory load and use it in the way that we used in our sender previously. So we access again a memory page depending on what value we get from this faulting load. And then this page is cached, and then we handle the fault. Everything is fine, and we can mount our flush and reload again over all these pages and see which one is cached. And this is then the value that we actually read from the line fill buffer that contains values of some other application. And with that, we actually leak values of other applications. So far, the theory. Problem one, we need two virtual addresses to the same physical page that we can access one and the other we can't access. That is luckily quite easy on Linux because the entire physical memory is mapped in the kernel. So every physical memory location has a corresponding kernel virtual address. So for every memory page, we get a kernel address that we obviously can't access. So we already have for every page another address that we can't access. So we simply need a normal page in our application. We can access that if we allocate one page, and then we just need to find the corresponding kernel address that also maps to this page, which we can't access, where this load will fault. All right, so shouldn't be too difficult, right? Let's again try that. So now we are in Zomyload. We have some victim here, quite simple victim that just takes one letter and initialize the memory with this one letter, and then in a while loop simply accesses that memory. So it will always be in the line fill buffer, and we kind of fill the entire line fill buffer with this one known value. So that makes it easier for us to see the leakage. So this is already done. We don't have to do anything here. We just need to write the attacker. So there's a bit more code, but most of that will already be familiar. We again have our cache utils here. We have the RDC, the flush, MXS, flush and reload, calibrate. Get one more function. That's just for the proof of concept to make it easier to get the physical address of a virtual address. And we need that to get this kernel address that maps to the same page. You again see here, we have this unblock signal, Segfault Handler, basically everything we just implemented previously to handle faults. Then we allocate memory here. So we get a mapping, one page. And for this page, we get the physical address. And then this magic comes in, physical address plus the offset of the kernel direct physical map. This is the starting of the address range that maps the entire physical memory. So if we add that here, then we have this kernel address. So target also maps to mapping, but using the inaccessible kernel address. So this is the mapping here, the magic that we get two mappings, one where we can access the page, and the second one that also maps to the page, but that we can't access. Then again, we calibrate our flush and reload, set up our signal handler so that we can handle all the crashes. And then we want to do the magic. And we do exactly what we have seen on the slides. There's one question in the chat again. The README mentions that one needs to disable KSLR to make the Zomyload work. Is this still true even when started as root? Yes. While we get the physical address, we don't get this offset. So this direct physical map offset is also randomized with KSLR. So you have two possibilities here. You can either, for the sake of a proof of concept, disable KSLR. Then this address is exactly this one. It's a deterministic address. Or alternatively, if we are talking about weaponizing it, for example, and we can't assume that the victim has that disabled. If you do an unprivileged attack, then we can use a different side channel, for example, echo load or data bounce to side channel attacks that can simply de-randomize the kernel and figure the address out for you. But we want to keep it stable here and easy. So I didn't add another side channel attack to figure out the offset. But for the proof of concept, we simply disable KSLR and then use this fixed address. That makes it easier. If you're talking about attacks, for example, on SGX, this trusted execution environment, then you're anyway in full control of the operating system. So disabling that is also in the threat model for a real attack. Okay, I hope that answered it. So if we remember our slides, then we said, okay, we need to have this complex situation where we flush it, the cache line, from the accessible mapping. So flush the mapping. Mapping is the one that we can access. And then we have the different side where we load the kernel address. So using the kernel address, load from this cache line, and again, encode it in the cache. So we again access the page in this shared memory that depends on the secret we leaked. So we have something like M access, and our memory is called mem. Yes. That is simply 256 pages of memory that we allocated in our application. So we're doing shared memory within our own application. And we access target. So we dereference target, which is the kernel address that maps to this page, multiplied by the page size added to the base of mem. So now we have this faulting load, and this line will crash. We don't want to do that. So we have to handle the crashing. And we already know that from before. We just save the program state here, try that, and skip it if we get the fault. And that should be it. So that should be the entire attack. So what happens afterward? The same as we already know from the receiver from before. We go with the flush and reload attack over all these pages, mem plus all the pages, check if one of them is cached, and if so, update a histogram, and then simply print a histogram and see what, like the distribution of the pages that are cached. Okay, let's see if that works. Now we can compile it, at least it compiles. Then we start here. So yes, something I've forgot to mention. We're leaking from a line fill buffer. So this is private to the core. This is not shared across multiple CPU cores. So we have to ensure that the victim and our attacker run on the same physical CPU core. So in case of hyperthreading, you can also run on the two hyperthreads on one physical core. So for example, here, if I run ls CPU minus e, then I get the cores that I have, my 4 cores and 8 hyperthreads. And I see here how the CPU core relates to the physical core. So what I see, CPU 0 and CPU 4, for example, are the 2 hyperthreads on physical core 0. Now I can use, for example, yes, 3 is already good, 3 and 7 hyperthreads on one physical core. And I start Zomyload here. Yes, for the physical attack. True. Okay, we see a histogram. Some values coming in. Nothing too interesting so far. Oh. Like that. And now on the other core, I start the victim. And as a secret, I don't know, let's use T. And if I start that, yes. Oh, I see that value in the histogram. I actually leaked that value because in the victim, I fill the line fill buffer now full with all the T's. And in the attacker, in the Zomyload, I can see exactly that value. I can also try a different one, like, I don't know, M. So yes, I'm leaking now only M's. Always a bit of noise. We see a few sets coming in and a few P's and things like that, because we're not the only application using the line fill buffer. All other applications running on this core also have values there. So sometimes we leak values of those. But for the proof of concept, we want to see something. So in our victim, we really fill the line fill buffer with always the same values so that we can clearly see them in the histogram. But everything you see moving right now are values that are actually loaded or stored by other applications. So we can really leak them here using Zomyload. It doesn't matter if it's a different application, if it's a trusted execution environment, if it's a different VM, everything that goes through the line fill buffer can be leaked using that attack here. And again, we see now that we built all these primitives from before, like flush and reload, with handling a signal, with encoding and decoding from the cache, creating Zomyload is super easy. So there are just a few lines of code, most of them copied from the last exercises, and it's basically just this thing we had to write from scratch. These 4 lines, these are the complex conditions that trigger the vulnerability. So with that, we leak all the data on the same and the sibling hyperthread. So everything on this physical core, from applications, also from the operating system, SGX, NGAs, virtual machines, from the hypervisor. So we basically just get all this data that is moved between L1, L2, and we simply get the values that move around there, no matter who loaded or stored the values. We have, of course, a bit of problem with the control here. As you can already imagine, we get bytes of data, but we don't really know where it's from. For Meltdown, that was easier. We specified the entire virtual address, read the memory from there. For Foreshadow, another transient execution attack, you specify the physical address and leak from that physical address. For Fallout, you can at least specify a page offset, but for Zombyload, also for a little similar attack, you only see the bytes and you can only specify the cache line offset. So you can only specify which out of the 64 bytes you get at which position this byte is in the cache line, but nothing more than that. Everything else, you have no idea where it comes from which application, when it was used, was it like super recently or already a few nano microseconds ago. So you don't have a lot of control. The histogram, yes. So let's switch back to code. Yes, so here we have the histogram. I can start that again. So here we see, so we leak the values from the line fill buffer, and we simply, with this dereferencing this kernel address that we also flush here, and getting the value, encoding that into our cache Covert channel, we encode the values that are still in the line fill buffer from some other application. And we make that visible using the histogram here. So for every letter, we are looking now only on A to C to make it fit here on the screen. We see how often we leak that value. And we can already see sometimes we have some bursts where we observe something. Exactly. It updated one I repeatedly, and now it updated some P, because other things are running as well on the CPU core. For example, the operating system. And if the operating system uses some data, loads, stores data that contains like here an I, a B, a P here, then we also leak these values. And that might not be text, but it could also be addresses. So that just means that this byte is an address, which is something that happens regularly. But if we now start a victim, for example, with the letter, well, is like U, for U, we've leaked one U so far. And if we start that, we leak a lot of U's, because our victim loads U's all the time from memory. So this will be in the line fill buffer all the time, and we leak a lot of U's. If we start the victim with G, then we see we leak the G's. But all the time we also leak some other values that are coming from the operating system, from the user interface, from some other applications currently scheduled on that core. From point of view of an attacker, I mean, now we are not working together with the victim. It's a completely different application that's not under the control of the attacker. So you can imagine that the victim is some crypto library, for example, that loads a cryptographic key. This cryptographic key consists of bytes. And now we start our Zomyload attack here. And if the bytes of the cryptographic key are loaded by the victim, then we see that in our histogram, that we see an increase in the key bytes. And then we know these are the key bytes. Maybe we don't know that from one run, but if is run repeatedly, for example, because the victim does an encryption and uses the key all the time, then we'll see that all the values for the key bytes increase the most. And then we know these are the key bytes. We don't know in which order they are, which we still have to solve here, but we know which bytes are in the crypto key. That already helps a lot. So here, attacker and victim, it's also why they are called victim, are not working together. And you really just see what this victim application loads from memory. So this is what we see here. And this parameter is it's just a letter that we let the victim leak, like we can do an O. And the victim does not communicate with the attacker. There's no shared memory involved here. It simply loads the data, and our attacker here, the Zomyload, can see what the victim loads as data. Also works for stores, so we can also turn it around. The letters essentially represent memory pages. Yes, yes, that is exactly still the mapping that we introduced with the Covert Channel. So we see that here we have a memory area that has 256 pages. And what we do here then for the leaking, we access depending on the value we load. So for example, maybe let's make that clear here. We can do something like mem plus, I don't know, u times 4096. So what would that code do? It takes the u, multiplies it by the page size, 4 kilobyte, and then accesses the uth page of memory, which has 256 pages. So now we don't have any leakage anymore. And if we run that, then we should only see, yes, fast, of course. Then we only see the U, because here we simply encode the U page, and then we go flush and reload. We check all the pages from A to Z and check if one of them is cached. And as we accessed the page U here, then we get the cache hit for this page U and update the histogram for U, add one to the histogram here. And this is why we get this nice line in the histogram here. So this is simply a mapping from values to pages by multiplying them by 4096, the page size. And here we don't use the U, but we basically can write that explicitly, of course. We say secret is dereferencing target, and then we use here the secret times 4096. And hopefully the compiler doesn't do something stupid, but then it should also work, and that might be easier to read. Okay, a lot of noise. Let's find something. Yes, but it still works. Okay, or E. Yes. So I hope this is now a bit easier to understand what we do here. Basically, if you don't want to write that mem access and we trust the compiler, we could also do something mem at the position secret times 4096, like an array access here. Probably could use that at some point. Volatile. I mean, maybe that works. Don't trust the compiler here. Okay. Yes, works. Nice, nice. Compiler is on my side. So we can also do it like that. Maybe that is even easier to understand than that we say, okay, we dereference the target, which faults. So here we only have transient execution. We have this memory array, and we access the page that depends on secret, so the value that we leak from the line fill buffer. With a pure side channel form, no. So you always, for these transient execution attacks, you always need a form of a covert channel to encode the values somewhere in the microarchitecture and then retrieve them again later on, because architecturally you can't see them. So you always have a transient execution attack. It's always some exploitation code and then attach a covert channel at the end of that to encode the value, first part, and then recover it later on. So with pure side channel attacks, we don't leak any values, we only leak meta information. But for transient execution attacks that use a side channel as a covert channel, as a building block, we can actually leak the values as we have seen here. All right. So now we still have this problem that we don't have a control over the bytes. I said, like, if we leak key bytes, then we get the bytes from the key, but we don't know which byte belongs to which offset in the key, or if it's even a key byte. So what we can then do here to solve that is kind of mount a domino attack, where we leak bytes and then shift bytes, so overlapping bytes. We'll leak like 1 byte, then 4 bits of 1 byte and 4 bits of the next byte, and then again 1 byte. And then, like the domino game that you might have played as a child, we put together the matching parts. We can match together the bytes and the half bytes here to build a chain that is probably the entire text here. And that actually works. So this is an example where we use Zomyload to leak the root password hash on a Linux system. So we see we have an application in the background that we can trigger that simply checks the password. It's something an unprivileged user can do. For that, it needs to load the password hashes into memory. And on the other core, we have our Zomyload exploit running that looks at what is read from memory, gets the values, and we recover the root password hash. So we had here the first 24 bytes. See the ground truth on the bottom after 1 minute. So this just takes a few minutes. And people also show that this can be optimized, that we can leak that in a few seconds and get the typically inaccessible root password hash using Zomyload. So that is a real weaponized attack then. So as a categorization, this Zomyload attack is a meltdown type attack. We've already seen in the picture. It basically uses meltdown and then adds this complex condition there. It has the basic mechanism. We have lazy permission checks, we have exceptions, and out of order after the exception. And this can be classified. And it's not only meltdown and Zomyload, but there are many, many more meltdown type attacks. So all the red nodes that you can see on this tree are different variants of meltdown type attacks where you leak values using or abusing exceptions that you can handle. And they leak from different sources, from the level 1 cache, line fill buffer, store buffer, load boards, store buffer, with different mechanisms and different exceptions that you can use. And that was only one example. So you can also find that online, that tree. You can look at that and filter and see what the other variants are. And for many of them, you will also find proof of concept code online. And now, as we have seen how one works, the others are quite similar. So it should be easier for you to also understand other attack codes. The final attack we're going to do today is a Spectre attack. This is not a meltdown type attack. We're not going to exploit exceptions, so we can forget the signal handling, this fault handling. We're now going into speculative execution. And for speculative execution, we're talking about branch predictions in most cases. So if you have an application, typical application contains a lot of ifs conditions, and they might be true or false. And sometimes the CPU cannot immediately resolve that because maybe the condition depends on some memory load. And that takes really long, as we've seen. Loading the condition from memory takes hundreds of cycles, and then the CPU can't continue. So this is a problem because the CPU doesn't like to wait. That wastes a lot of time. So what the CPU does is, for these ifs where the condition is not resolved, it simply predicts the outcome. It can only be true or false anyway. So the CPU uses the branch predictor to predict the outcome. And this branch predictor is based on events from the past. So if this if was already executed many times and in 99% of the cases it was true, then the CPU is going to predict that it will be true again. And that is in many cases correct. And then the CPU can already execute the parts that will likely be true. And if the condition is resolved, then that is fine, because then it's very fast and we didn't lose any time. We didn't have to wait. If the prediction was wrong, on the other hand, then yes, the CPU executed something that was not necessary and it has to discard the results, similar to an exception, and then clean up. So we already have that mechanism in the CPU anyway. The speculative execution basically relies on out-of-order execution, because we already do that. We execute things without knowing whether they should be executed. We've seen that with exceptions. Now it's by predicting where to continue. And if the prediction was wrong, these instructions that have been executed, they simply have no effect. We don't ever see them. But of course, you guessed it, we see that in the microarchitecture. That are also transient instructions. Also, if you're talking about speculative execution, what happens if we speculate and in the speculation is an exception? CPU doesn't know if the speculation is correct. So again, this is only marked and only checked at retirement. And only if you really execute that part, then if the speculation was correct, then it handles the exception. Otherwise, it cleans it up anyway, and this exception never occurs. So this is also something that we can use instead of the signal handling to handle a segfault, to simply have the exception somewhere that is a mispredicted branch, then it also never occurs and never crashes our application. But we don't care about that here for Spectre. That's just an interesting side note. So if then the condition of this if is resolved and everything was correct, then the instructions that were speculatively executed retire in order and they become visible. Potential exceptions have to be handled. If the prediction was wrong, then they're just removed, everything is cleaned up, the speculation is undone. And that is a nice optimization, because if we have something, a prediction, for example, if something is in bounds of a buffer, if we can access that, if it's actually in bounds and it's predicted to be in bounds, then it's fast. If it's predicted wrongly, that is false, okay, then it's slow, but it's not a problem, but because we still stay in bounds. If something is not in bounds and we want to access that array index then, for example, and it's predicted to be not in bounds, is also great. It's also fast then. But then we have one remaining case. If a memory access is not in bounds and the CPU predictor predicts that it's in bounds, then we can actually exploit that to leak values. This is what we are going to do. So for the sake of completeness, it's not only the ifs that are predicted, but there are many different predictors. So we have for the if, the pattern history table, but also for indirect jumps, indirect calls, we have the branch target buffer that predicts where to jump to. We have a return stack buffer. If you return from a function, it predicts where to return to. And we also have memory disambiguation that predicts whether there are certain dependencies between memory values. But we're only looking at one variant in this tutorial, Spectre variant 1, Spectre PhD, exploiting these bounds checks. And again, we have our shared memory, can be shared within our own application here for example, but again, shared memory consisting of 256 pages. And then we have our Spectre gadget here with an if, with a bounce check, and some memory. So what are we going to do in this code snippet? We have memory in our application, data that we want to access, 4 bytes of data, and after that, a secret key that we are not supposed to access. That's why we have this if here that checks if the index we want to access is smaller than 4. Then we access data at the position of index, so either D, A, T, or A. And then we access a memory page here in the shared memory, depending on the value that we read from the memory. And if we do that, so the CPU at first has no idea if this condition is true or false, encounters it for the first time, might speculate that is not true and executes nothing. Then it resolves the condition and sees, oh, it was actually true, 0, index 0 is smaller than 4. So we can safely execute that, fetch data at 0 from memory, it's D, and then access the shared memory at the D page and cache that. Then we provide index 1. It speculates it was true before, must be true again. Speculates already speculatively, does all the things, access the memory, access the shared memory, depending on this memory, caches that, and it learns when resolving the condition, speculation was correct, perfect, nothing to do anymore. Index 2, the same. Index 3, the same. Index 4. 4 is not smaller than 4. CPU doesn't know the condition yet, the outcome of the condition. So it says like the last 3 times this condition was true, so it speculates again, it will be true. Accesses data at index 4. But this is already out of bounds and accesses a secret key there, the K, and then uses that K, accesses shared memory for this K page, which is then cached. And that already gives us out of bounds values. Because we already know we can now mount a cache attack on the shared memory, see K is cached, and we know that the first byte of the secret key is a K. Then the CPU figures out, oh no, this condition was now false. So it was misspeculation there, cleans everything up architecturally and executes the else branch, but the cache is not cleaned up. So we already see we can again encode secret values into the cache and recover it later. Just need to convince the CPU to misspeculate here. And as these prediction structures use virtual addresses and only parts of virtual addresses, we can kind of easily do that because different branches at different locations map to the same index in this prediction table. And also with virtual memory, we have the same virtual address in many applications. So we can influence the prediction of a branch in one application by a different application by simply taking or not taking that branch in our other application. So let's look at how that works in code. So we have the Spectre here. And again, a bit of boilerplate code around that. We again have 2 memory areas, again 256 pages of memory that we use for encoding. And then we have here an access array function that accesses the string, first hello, the thing we can access, and then our top secret key, like in the animation before. There we have a condition check that checks if the index is below 5. Why there are these weird divisions here? Just for the proof of concept, to make the condition more complex, so that it takes longer, that we have a better chance of actually mispredicting. But that just makes the proof of concept more stable on a wide range of CPUs. And then we have exactly that. We access the string at the index, and then again access memory at this value that the string had and at this string secret page. So same as before with Zomyload. The encoding is always the same. This is our Spectre gadget here. And if everything is in bounds, we also then return the value here. Otherwise, we return 0. So So we can't access that. Then we initialize all the memory where we recover the value. Then we try if that really works. So we try to architecturally access the secret and see if we get the value or not. And then we mount our actual attack. But first, let's try. We build that, execute it, and we see architectural access. We only get the hello. The bounds check works. We really can't access anything that is out of bounds. Even though we try to access 15 characters here, we only get the first 5. All right. So what do we have to do next? We have to mistrain the branch predictor. So we have to make it believe that this access checks, this bounds checks is always true. So we call it sometime, a few times. Let's try work here 10 times. Call the access array function with index 0. 0 is in bounds. So the CPU learns, okay, we access 10 times now in bounds of this array. So this condition will likely always be true. So this is the mistraining part. Then we want to have the actual out of bounds access. So now we access array and code then into no, it's called here, I think. If I remember correctly. LOT, yes. I should unify that at some point. And now we access the characters. We have this loop over all the character from 5 to 15, so the inaccessible ones. And we want to access this character now, this inaccessible thing. We already told the CPU like it's fine. We always access in bounds. Next time speculate. That is also true. And then we provide the out of bound value, the character value that we want to leak. And then it's again encoded in the cache. And now I can write the recovery again. We go over all the pages. And you already see there's a kind of repetitive pattern here. I'll use the prefetcher a bit. Then if off. And I'm only interested in letters A to Z because everything else is not in our string. And that makes it a bit faster. And we don't have to do that many flush and reload attacks. And then we flush and reload, lookup table, offset times page size. That is smaller than cache miss. So if a cache hits there, then we can say recovered at position recovered index. Then we know at this index, this letter is the correct one that we recovered. Okay, did I forget something? I don't think so. Let's see. Does it compile? Compiles. Nice. And now I run that. And we remember before that we had architectural access hello and then nothing. And then we, oh, wow, first try and it worked. So we see we actually now recover this top secret values. So there's one question from the chat. So the divisions in the if branch are really so computational heavy that they take more time to execute than the memory access of the Spectre gadget. Yep, exactly. Because the special thing here about the division, there are also floating points divisions. So these things have to be converted to floating points, and then it calls the floating point division, and then it converts it back to do the comparison. So you can also look at the object dump here. We get many instructions that have to do the conversion, the division, conversion back. And that is computational quite heavy. That takes time. That gives us enough time to actually do the two memory accesses in here. So yes, everything that makes the computation more complicated, and we're only talking about a few cycles, it doesn't have to be a lot, increases the success rate. So I don't know how well it works if I would remove that here on the CPU. it still works. So far not. Yeah, on this CPU, we've seen it in the cache histogram as well. The memory is very slow compared to the CPU. The CPU is very fast. So we don't have a large time window here, so we would have to optimize that a bit further. But it is, of course, possible without this weird divisions that just makes it more stable to test it everywhere. But of course, also works without that. Then we just need a bit more of engineering. We can do different tricks like flush the code where the condition is located and things like that, and also makes the execution slower at this point, or just try more often. So yes, we have seen Spectre also looks similar, right? We do an access, we encode in this memory area, and we recover using the flush and reload. Just now using mispredictions by confusing the CPU first, and now we don't have any exceptions that we need to handle. So we've also successfully written our Spectre proof of concept that leaks this top secret inaccessible value here. So this is, of course, also something we have to prevent, because that leaks data from other applications. And for that, CPUs introduced some new instructions and settings that can control the speculation behavior a bit, so that it doesn't work across applications anymore and across hyperthreads. That now exists on Intel and I think also AMD and ARM CPUs. So we have a bit of more control over what is used in the speculation, what not. We can even disable now some forms of speculation that speculate on memory dependencies, but still, this is not a full solution, because none of the solutions here affect anything what we did here in the proof of concept. You can enable all of them, and I think I even have all of them enabled. They don't prevent the exploitation where you mistrain this branch and then abuse it. They only prevent that if you try to mistrain it in a different application, which is even a more complicated exploit. But this one is not prevented. The only realistic thing we can do here as a mitigation is to add serializing instructions on branch outcomes. So we can abort the speculation of the CPU by adding fences again. But of course, we need to know where to add them. So this is also not a trivial thing. And if you add too many fences, then we lose a lot of performance. Parts of that are automated now. A REDPO line, for example, does that for indirect calls. So they already fenced that correctly in a compiler, but everything else is still something that a developer has to do, and that is complicated. So it's still not a fully solved problem. RSP for return, we have some solutions for that as well, but typically only to protect the kernel. So we can still show like fences are, if we know what we're doing, we can easily prevent the attack. So if you go back to our code and we have this working Spectre, so we know our Spectre gadget is here, our branch is here, and we can insert a fence here. And this L fence stops the speculation here, and we don't go into the speculative memory access. And if we compile that now and execute that, the leakage is gone. So this is something that we can do as a developer. For example, if you're writing a crypto library, that we can stop the speculation. If we remove it again, then it should again, yes, leak the value. So this is something, but we have to know what a Spectre gadget looks like, where we can find it. We have to be sure that the compiler doesn't do weird things like introduce more Spectre gadgets on its own during optimization. So this is also not a perfect solution. But at least if you know what we do, we can prevent the exploitation using Spectre. So at the end, the big picture. So what was known already for quite some time is leaking values, mounting side channel attacks on branch predictors. These are branch predictor attacks that figured out from other programs if a branch was taken or not taken and infer the control flow. Spectre then showed we can inject something into these branches and make the CPU take or not take this branch. We've seen that we've mistrained the CPU and made the CPU take a branch that it should not have taken. So this is like the other part to this branch prediction. Side channel attacks. We've then seen Zomyload, this meltdown type attacks that leaked using out of order execution and exception handling. So we had these exceptions, and then with that we leaked value. And then there's the other attack I briefly mentioned in the beginning, that's load value injection, LVI, that also turned this effect around then. And is also an extremely powerful attack because that does not use exceptions to leak values from other applications, but that can use the exceptions to inject values into other applications. And these other applications then use this injected value. And with that, we can again modify their transient behavior. So we have now this nice 4 squares here with all these different types of attacks, from which we have seen the upper right one with Spectre and the lower left one with Zomyload. And these are not the only ones, of course, there are many, many more, but we only have limited time for these things. But what we've seen so far and what will hold for the future, so these transient execution attacks, they exploit problems in the CPU. For meltdown type attacks, there are actual vulnerabilities in the CPU. They are getting fixed in silicon with new CPUs. For Spectre style attacks, they are due to the design of how we design CPUs, so they cannot be directly fixed. They are not bugs. They are a design, like cache attacks. We want them to behave that way. We want to have branch prediction, so we are not easily getting rid of them. We've also seen, if you've tried the example, all operating systems affected, of course, because these are effects on the CPU level. There's also nothing that can be fixed on the operating system level. And this is a very new class of vulnerabilities that was first discovered only in 2017. And we made that public in 2018 after embargo. And since then, basically every year, we see new variants and new types of these transient execution attacks. So this is a pretty new topic. And I hope that I've given you a bit of an insight and the code examples to see how they can be mounted, that you can now also try to mount them yourself, understand code if you find that somewhere, and also do some research and maybe find your own new variant of a transient execution attack. Because likely we haven't discovered all of them, and there will be more to come in the future. All right, so that brings me to the end of today's tutorial. You can, of course, ask more questions, write me an email, whatever, write me on Twitter. If you're interested in some more things, more descriptions of the things, more attacks. So I've also added here at the end some references that you can check out about papers about transient execution attacks. There are quite some things on them, academic works, presentations, vendor white papers, deep dives. So there is a lot to read if you're interested in that topic. And also for many papers, you will find some proof of concepts online that you're now hopefully able to understand a bit better after having seen what the important building blocks of these attacks are. All right, so if you have questions, you can still post them here. Otherwise, this is the end, and I hope, yes, you learned something, had some fun. I was not too fast, it was not too boring. So thanks everyone for being here, and I hope I answered all your questions. Okay, there are no more questions. Then I'm done. I don't know if there's any. Linda, if you want to add something here, or
no, thank you very much, Michael. This is really interesting. And yeah, for everyone who wants to maybe rewatch or recommend the tutorial to anyone else, it will be online in a couple of days, and you can on the Athena Center YouTube channel, and you can either follow the ESORICS Twitter account or the Athena Center Twitter or LinkedIn. I think it will be published there as soon as it's online. Yeah.
okay, thanks a lot. Then
thank you.
Have a great afternoon and bye.